Welcome to the Knowledge Graph seminar. Today, we are in the week 8 of the course, where our focus is on how to evolve a knowledge graph. Today's discussion will focus on one aspect of that problem, which is how do we meet the challenges of creating large knowledge graphs that are going to last over a long period of time. In the series until now, on Tuesday, typically I've been giving my synthesis lecture, but for this week, my synthesis lecture will happen on Thursday. But for today, we could not have hoped for better speakers than Dr. Luna Dong and Professor Deborah McGinnis. Luna is at Amazon, and she is the person behind Amazon's product knowledge graph, and she's going to tell us about some of the issues they have addressed in the process. And Professor McGinnis, she's the inventor of the web ontology language, which is used all over the place these days. And this is a work that she did when she used to be at Stanford many years ago. So it's really a magical moment personally for me to have both of you here. So with that, I will hand it over to Luna. Please take it away.
Thank you. Okay, so let me share my screen. Can you see my screen well?
Yes, we can.
Okay,
Perfect.
Great.
Yeah.
Thanks a lot for the intro. Hi, everyone. I'm Luna from Amazon. It is my great honor to speak here to tell you about our efforts to build a rich product graph, and I call it 0 to 1 billion. Some of you possibly have heard or read the book From 0 to 1, 0 to 1. And so it is very exciting to have a startup, but let me tell you, it is even more exciting to build a huge knowledge graph. Okay, so we have been halfway through the course, and you all know very well about knowledge graph. Here I want to use an example, 2 examples to show you what is the difference between a generic knowledge graph you have in mind as you observe Google, Bing, and what is a product knowledge graph. So here is a generic knowledge graph for 2 songs. So it is a graph, so we have nodes and edges. Each node represents an entity which could belong to one or multiple different types. For example, this is a recording, and this entity on the other hand is a genre entity, and an edge represents the relationship between them. This recording has this particular genre, and the name of that genre is country pop. And similarly, this recording has the same artist and the songwriter whose name is Taylor Swift. So this is a knowledge graph we are all familiar with. And here is an example for a product knowledge graph. So here at the center, we have 2 brown bubbles representing 2 consumables or detergent products. And then those green bubbles represent their variations, other Tide detergents with different sizes, different scents. And then we have their product properties, such as the brand, the function, the form. Both of them are liquid. Neither of them is high efficiency. And for one of them, we have an extra function, odor remover. Okay, so with such authoritative product knowledge graph, we wish to answer any question about products and related knowledge in the world. We hope to use it to improve Amazon search, recommendation, and voice shopping. To be a little bit more specific, so let me show you some of the use cases. We use this structured knowledge to provide information to make it easier to understand a product. We use it to provide choices. For example, you can see different styles, different flavors, so make your shopping choice. We use it to improve search. When you search for K-Cups Dunkin' Donuts dark, we know you are asking for dark roasted, and so something that is medium roasted is not right. And similarly, even though you ask for donuts, Donut Shop is not the right brand. So we want to replace them with the right products you are searching for. And finally, we also want to use it to improve recommendation. So when you are trying to buy some mixer, as an example, we can show you other mixers with higher capacity, with more attachments, different brands, so on and so forth. Okay, so now quiz time. You have seen a product graph, you have seen a knowledge graph. What is the relationship between them? Is a product graph a small piece of a generic knowledge graph? I can't see your answers. You can write down your answer. So is it a subset, but not so small piece, but a bigger piece? Or it's actually overlapping. So some part of generic knowledge graph, sorry, is not product graph and vice versa. So I don't know if you have written down A, B, or C. If you haven't written down anything yet, I know your answer must be D. So nothing should exist if Jeff Bezos does not sell it, right? Okay, so the right answer is C. For a lot of generic knowledge, like movie, music, and books, they are part of products, and vice versa. For products, on the other hand, we have a lot of furniture, electronics. We call it hard line. We have clothes, shoes, purse. We call it soft line. Consumables are those products you put in your kitchen, in your bathroom, and those products so far are not necessarily included in the generic knowledge graphs at Google, at Bing. So that's quite specific for the product domain. And let me describe to you our product knowledge collection pipeline. External name is called AutoKnow, and we published a paper last year at KDD. So it takes the taxonomy, the product type taxonomy tree as input. So at Amazon, we already have some taxonomy. Also at Amazon, we already have some catalog. For each product, we know the type, we know some of the attribute values, such as the flavor and color. And green values are correct. Red values represent erroneous values. And for some of the values, we might be missing for some products. And in addition, we have the customer behavior logs when they do the search, when they click, following the recommendations, so on and so forth. And using our pipeline, we want to generate a product knowledge graph like this. We do still have this taxonomy tree, but we add new types. For example, we found pretzels as one more product type, and that's a subtype of snacks. And we backfill new values. So for example, for product 2, we found the flavor also makes sense for it, and we find the flavor of this product. We fix wrong values. Cherry is not the correct flavor for product 1. Instead, the correct value is chocolate. And we also find the synonyms. These are just the 2 different ways to say chocolate. So that's kind of what we are doing in building this product knowledge graph. So in our system, up to last year in the prototype, we increased the number of types by 3x for the consumables domain. And we reduced the defect rate caused by missing data or incorrect data by up to 68% point. Okay, so that gives you a rough idea what we are doing. And at this moment, you might be considering, okay, is this problem really much harder? We know how to collect knowledge for generic knowledge graph. We saw the success from Google, from Bing, etc. And do we just apply the same techniques for this Eclipse to collect information about products? It's not that easy. And there are several unique challenges in the product domain. The first one is in the product domain, the data are typically provided by the retailers, and the structured data is very, very sparse and very noisy. So here I'm showing you a screenshot from Amazon. And you see for this like candy box, you get very, very little structured information. It's really just more of the title. Everything is buried in the titles, descriptions, and so on. On the right side, we do see some structured information such as flavor and sizes. But on the other hand, you possibly wouldn't call red rose box as a flavor of your favorite chocolate. You possibly wouldn't call dark blue foils as the size. So those information can be very, very noisy. The second challenge is that we have extremely complex domains. We have many different product types. And actually, I can give you the number. There are millions of different product types. And so we want to understand what are those product types and what is the subtype relationships. In other words, how to organize them into a taxonomy tree. So taking knife as an example, if you talk to the sellers, what they have in mind is they have a kitchen and a dining sort of department. They have a sports and a fitness department. And in kitchen and dining, they have a sub-department, which is cutlery and knife accessories. And under that, we have chef's knives, bread knife. And in sports and fitness, we have a sub-department hunting. And from there, we have knife sets, hunting knives, and so on. As customers, what we want to buy is really just a knife. And here is the view from the buyers. And how can we sort of align the seller's view and the buyer's view and build this taxonomy? Third, when we have these millions of product types, we actually have huge variety. And first, with all of those different product types, we actually have different attributes. And if you don't understand that, you could make mistakes. For example, here is a pretty, lovely dress for a girl. And if you don't really understand what attributes are applicable for girls' dress, and then if you work very hard, here is what we did. We say, okay, the flavor of this is cranberry and the ingredient is sunflower. Another thing is for different product types, for the same attribute, the values could be very different. And we see them in different context patterns. So here I'm showing you a TV set and a tea box. For size information, we see that the vocabulary is very different. And also, if you read the context surrounding this value, it is also very different. And then now you might say, okay, tea and TV, these are so different. And I understand, but I'm sure there are a lot of, most of the, I mean, we can sort of put those 1 million product types into a few categories, and within each category is fairly similar. Let me give you another example, which is coffee. Tea and coffee are two nodes that are siblings. So both of them are subtype of drink. So they are very close to each other. But if you look at the size of tea box and the size of coffee, again, it's very different. The language is totally different. So this huge variety makes it very different, very hard for you to be able to manage all of the different domains. So even if we are able to build a good model, we still need to scale it up. We need to scale it up to thousands of attributes. We need to scale it up to millions of categories. And we need to scale it up to hundreds of languages. With all of this, it's hard because it's a lot of models, a lot of space to take care of. And meanwhile, the key challenge is we have limited training labels for so rich and diverse data. Okay, so with all of this being said, I remember 5 years ago, nearly 5 years ago, when we did a demo to our SVP showing the power of a knowledge graph. And he asked us how we collect the knowledge. At that time, we only have Tide detergents. So we told him the details, and then he said, wow, this is a 100-year project. And so the question is, now we need to deliver this data business. We want to cover all of the data, but how can we finish this 100-year project? And here I'm using 1 billion as a symbol to say a lot of data. And to get so much of data and to finish this 100-year project, certainly what we can do is we really exercise hard and we try to live 100 years longer. Indeed, that's not what we are good at. And so what we are trying to do is to do it in steps. And to get to 1 billion, the first thing we need to go from 0 to 1. And here what we need are high precision models that give us accurate knowledge. And this is a critical first step. Note that even though you see a lot of zeros here, which means you have large scale data, but if you don't have this one high accuracy as the first thing you get, then all you get is a bunch of zeros. In other words, you get nothing. Even if, let's say, we have 90% accuracy, it means every 10 data items you provide, one is wrong. This is barely acceptable in industry, in real setting. So 90% is almost the minimum. And then to go from 1 to 1,000, I mean, you have your beautiful model and you are very proud of it. And if you are writing a paper, you're possibly done. But in practice, that's just a first small step. And because you want to do a lot of data, you possibly need to train quite a few different models, and you possibly need to sort of apply that models many times. And so you definitely need some end-to-end pipeline, and also you want to have auto ML to reduce the modeling cost. After that, how to go from 1,000 to 1 million? Recall that we have here, I already scaled it down a little bit. We want to handle a minimum of thousands of categories, hundreds of attributes, and tens of languages. If we develop the models for every category, attribute, language, it means we need to train and maintain millions of models. And so if we truly want to scale up, we need to reduce the number of models we need to train and maintain. This is where we use transfer learning. We hope one size fits all. And that's where we need to really be creative. And finally, not only we want to cover all of this space, for each single cell, we want to deliver a lot of data. We want high recall. So far, you haven't heard of me saying recall. And when we want to go from 1 million to 1 billion, that's where the recall kicks in. We want to have high yields and high recall. And here, we certainly want to improve the models. We also want to explore all different sources, not only text, but also images. This is where multimodal models kick in. And also we want to get the data from the web. Okay, so let's now see what we have done for each of these steps. So from 0 to 1, as I said, we need high quality data. And that calls for high precision models. And let me just use the example of filling missing values as an example to show you one model we have developed that could extract the correct knowledge. So here the question is this: for a whole bunch of product titles, we want to extract from it the attribute values such as the detergent form, liquid or powder, and the detergent scent. So for example, from this one, we know the form is liquid, the scent is apple mango. From this one, just from title itself, we don't know. So that's the problem we want to do. This is a knowledge extraction problem. Oops, okay. And we solve this problem using tagging. And this is BIOE tagging. A lot of you possibly have heard of it from NER, name entity resolution. And what we do is we take the input, beef meal and ranch raised lamb recipe. And then let's say we try to figure out flavor. The first flavor is beef meal. And so beef is tagged as B, beginning. Meal is tagged as E, ending. And then the second flavor is ranch raised lamb. The first is ranch, tagged as B, raised inside, so tagged as I, and lamb, tagged as E. And then this end and the recipe, this is not the flavor, so it is tagged as O. So we did a 4-layer NER model where we take the word embedding as the input, and then we apply BiLSTM to take care of the sequence of the input, and then we apply attention, and after that we apply CRF, conditional random field. So we output BIOE models and take care of the correlations among them. For example, E should appear after B. So this gives us the first model, and we see that adding the CRF and adding the attention will give us the best results in terms of precision recall. And the nice thing here is that the model is called OpenTag because we can identify new values we haven't seen from our training data. So here the gray bar represents the values we have never seen before, and dark bars represent all of the values. We see that for the unknown values, even though the quality is slightly lower, but not too bad. Okay. So far we have some reasonable models giving us reasonable results. Look that at this moment, the precision is not 90%. Recall that I said we need a 90% precision. To bring it to production, we need to do a lot of things. So we first need to generate the training data. And deep learning models are typically very sort of data hungry. And so we need a lot of people understand the domain, the attributes, generate a lot of training data. And with the training data, some scientists could come in to train and fine tune the models to get good results. And after that, if the quality is not good enough yet, it's not 90% yet, then we need some people to look at the data, look at the results, and do some post-processing. This is oftentimes rule-based, and then we further improve the data quality and remove the noises. And finally, we have a whole bunch of extracted data to publish it, to catalog, et cetera, knowledge graph. We need to do some pre-publish evaluation and as gatekeeper. And that again needs a lot of people to do the evaluation. Basically, we sample and do the annotation saying yes, correct, or no, incorrect. And keep in mind that this is still the origin point in our 3-dimension sort of space. Okay, so that's our starting point. Next, to go from 1 to 1,000, we need to reduce this modeling cost. It's too many people we need to use to deliver the model. And here we need some pipeline that could help us to reduce the manual work. Let's see how we can do it. The first thing we want to do is, instead of manually generate a lot of training data, we can apply weak learning. So we use distance supervision and data programming, and that allows us to automatically generate the training data. With that, it's not that all of the training data could be automatic and we can definitely sort of remove people out of the loop. We still need some benchmarking data for us to understand the quality of the results and possibly to do some fine tuning of the hyperparameters. Next, what we can do is this. So we developed some deep learning data cleaning model to identify wrong values extracted by our models. And with the post-processing, with this deep learning cleaning, we are able to remove a lot of noises. It may not be all of the noises, so we still need to do post-processing, but now we need much fewer people. And finally, for the evaluation, we try to scale it up as well. So we could just sort of evaluate for every single attribute and product category with less samplings, but with the same sort of statistical significance. And with all of this, we add AutoML. And now instead of having the scientists training the models, we can have some like data associates training the model. So that is the end-to-end pipeline, including both training and inference, that allows us to scale up. And here I want to say a few more words for this deep learning model. You might be curious what we are doing to identify the mistakes. Basically, what we want to do is to look at the titles, the descriptions, and decide if a value is correct. For example, whether pink is a flavor. And if we see the title said mint chocolate, and also seeing that from descriptions, that's where we will feel, this might be a wrong value. So we feed in the data, including the title descriptions, and also the target attribute value into the transformer. And then we basically output yes or no. I do want to point out, and here, that we also put the product type of this product in this as one part of the input to the transformer, which gives us better results. So I mentioned the transformer here for cleaning, but BioSDM for extraction. So that's mainly because at the time when we published that paper, which is a couple of years ago, we used BioSDM. Later on, we tried transformer, which did not give us better results. Only very recently, we used transformer model for multilingual extraction. Okay, so here are some of the values we identified as wrong values. For example, pink flavor, color one flavor, this 2 package as scent, and this help us like identify 1.8 millions of incorrect values for flavor and scent. Only these 2 attributes, we identify so many incorrect values. And the precision is 90%, meaning every 10 values we identified as incorrect, 9 of them are indeed incorrect. Okay, from 1,000 to 1 million, how we scale up. And let me talk about how we can reduce the number of models in this like category dimension. And this allows us to train one model, hopefully for hundreds and even thousands of different categories. And recall that using size as an example, different categories, they use different patterns and vocabulary. And we also see that for some of the sort of long tail categories, we have very little training data, even if we wish to train this like millions of models. We don't have the training data for it. And here is what we did. So on the left side, we have OpenTag, as we just presented. And here what we do is we take category as the input and use that to generate the attention for our results, for our model. And then the second thing is we do multitask learning. So in addition to extract the values, we also try to predict the category of the product. And this allows us to identify key tokens in the title that tells us the category of the product. So with this attention condition on the category representation, we are able to improve the F measure of extraction by 10 percentage point. And at some examples, like for this one, this is so using our previous model, we are not able to predict the flavor, but using our new model, which is taxonomy aware, we are able to say, hey, the flavor is purple lemonade. Another example is this eyeshadow. We could say palette is the scent, but once we know, hey, this is eyeshadow, then we would not extract any scent. Okay, so the second dimension we do is we also try to train one model for different attributes. And here is an example where it shows you just from the descriptions and titles, we actually see not only one single attribute, but multiple different attributes. And in our model, this is the same way to show the 4-layer model. The naive way is for every attribute, we need to train a model. And then the number of models will be the same, the same as the number of attributes. And what we did is we add an attribute embedding layer. We take the attribute name and generate embedding for it. And then we use mix of experts and HyperNet to generate the parameters for the CRF layer. And I wouldn't go to all of the details, but you could think of different experts take care of different attributes. And then we sort of look at the new attribute and look at its similarity to existing attributes, and then try to sort of get a weighted combination of the parameters. So
we have roughly 5 minutes left.
Okay, sure. So with this, we're able to train one model for 32 attributes. And you can see that this is the baseline results where we train one model per attribute. And using our models, we can even beat that results. Okay, how to go from 1 million to 1 billion? And here we need higher yield. I will just tell you a little bit about how we do multimodal extraction. So this is a paper recently just accepted at KDD. And so basically with this product, we want to know the item form. From the title, you see stick, you see cream, you see powder, and you can be very confused. But if you look at the product image, you would see, hey, here it says stick and in the text, and meanwhile, the shape is like stick. What we did is multimodal transformer. I don't want to go through all of the details. It takes the input from text, from the OCR results on the images, and also from the image embedding. And then it trains a generative model where it takes the output text from the OCR text, from the product's descriptions, as well as from the dynamic, the vocabulary of the values, and then get the results. So we will skip the details. And just to give you a sense how well it performs, so if it compares with OpenText, which look at only the text, it improves the F measure by 11%. And we could drop text or image or OCR. All of them give us lower F measure. And here, text contributes most. Dropping it will give us the lowest F measure. And image contributes least because most of the information is actually already in OCR text. And I do want to mention one other thing, web extraction. And so I won't tell you all of the details, but from this, you can see that these are from different web pages, websites, and we can also get all of the sent item form and so on. And when we get data from the whole web, we could enrich the data we could extract. Okay, so we have been doing this project for over 4 years. And for the retail domain, so far it is about 2 years. One thing I want to say is there are many, many subfields for knowledge graph. And what are successful in industry, as I have observed, and what are not so successful. So I have seen a lot of successes for entity linkage, deciding whether that's the same product. For knowledge extraction, we have talked a lot about extracting the knowledge. For knowledge cleaning, trying to identify mistakes, and for knowledge-based question answering, etc. And for some field to be successful, typically there are two things to make it happen. The first one is you just cannot live without it. You have billions of products. You cannot manually say, hey, these two products are the same and that two are not the same. There has to be some automatic way. And the second is the techniques are fairly ready. And for data business, it typically means you have fairly good precision and reasonable recall. On the other side, I have seen subfields where I haven't seen much of success yet. There might be success in future. For schema mapping, as an example, if you want to decide directed by and a director are the same relationship, this seems to be an important sort of task. However, I have been observing manual work for small scaled ontology. And once it is large scale, you need to go to the web. Then instead of doing the schema mapping, people just replace it with closed information extraction, closed IE. Another one is OpenIE, which is a very hot concept 10 years ago, where you extract the knowledge without aligning it. And so far, we haven't seen real practice in industry. And it is much more of a being replaced by reading comprehension. Knowledge fusion is another field where you get data from different sources, you try to resolve the conflicts. And so far, people are not very successful yet in terms of getting all of the knowledge from the web to put it together. It's just a starting point still. So that's why for this one, there are a lot of research, but it is not fully needed yet. And another example is knowledge inference. You use knowledge embedding to infer new triples. So far, as I see, the quality is not high enough for industry to really sort of deploy that. Hopefully, we will get better results, especially for those stuff that is needed and are not sort of replaced yet. Hopefully, we can improve the techniques to see real success. With all of this, I would like to conclude my talk. We are building an authoritative product knowledge graph for millions of categories, thousands of attributes, and hundreds of languages. And to make the first step, we need some high accuracy models so we can build, we can collect accurate knowledge. And then when we want to enrich the knowledge and scale up, we need end-to-end and possibly AutoML pipelines. We need some transfer learning, one-size-fits-all solutions. And we need multimodal models to get data from all available sources. Okay, thank you very much.
Awesome. Thank you, Luna, for that excellent overview. Deborah, over to you.
Thank you.
We'll have time at the end for discussions and questions.
Sure.
Yeah. Okay, so I'm going to try sharing screen and and I should turn my camera on. So do you see
yes
designing knowledge graphs? Okay, so I'm going to do from the beginning. All right, so now you see the full display.
Yes, yes.
Okay, and you don't see the next slide thing, right?
No, no.
Okay, because I see that. Okay, so I'm really excited to be presenting today. Thanks very much to the organizers for inviting me. This kind of feels like Old Home Week because I sat in the Gates building for 12 years or something like that before coming to RPI. And today I'm going to talk about designing knowledge graphs that last. And actually, it's a really nice complement, I think, to the talk that Luna just gave. So just to give you a little bit of background on me, I've been hanging out in knowledge graphs, ontologies, and provenance for many decades, all mostly as an academic. My first 18 years were at AT&T Bell Laboratories, where I did more foundational work around description logics, which are kind of at the formal foundations of the ontology web language that Vinay mentioned earlier, or just ontology languages in general. But I also did some number, despite the fact that I sat in the pure research arm, I did some number of large applications, and some of which were still running 14 years after we put them in place when I left, and I don't know how long they worked after that. And they were configuring large pieces of transmission equipment, but using essentially knowledge graph and ontology technology under the hood to create complete and correct parts lists. So in my AT&T days, I did kind of long-lived ontologies and knowledge graph work. And there's pictures of wine there because actually, oddly, my longest lived system, ontology and application is a wine and food pairing system that I did initially in a graduate class I'm exposing how old I am, in 1984, when I was taking an expert systems class at Rutgers while I was actually on staff at Bell Labs, trying to figure out something that I could pose as an expert in, and I'm a wine and food connoisseur. And that set of rules that later became an ontology, that later became the foundation of an Ontologies 101 paper that I wrote when I was at Stanford, actually literally 20 years ago today, and is at the base of a lot of example systems, including some number of the World Wide Web Consortium documents on how to use an ontology language. So this thing that I did as like a second year graduate student lived on for decades. And I'm going to reflect on some of the properties about that I think we might replicate. Like I tried to replicate those properties today. Also, I'm somewhat famous for, actually, I don't know whether you see my pointer, for this ontology spectrum. I and 4 other people at a AAAI, again, showing how old I am, in 1999, we're on a panel about ontologies. Are they just expert systems all over again? And so some number of us ontology experts met for about 4 hours the night before saying, what do we actually mean by ontology? Do we just mean a controlled vocabulary? Do we mean a much more logically precise and expressive language, or do we just mean something in between? So we're going to talk some about what constitutes an ontology, and then what constitutes an ontology that we might be able to use for a long time. So those are just a few things that I've kind of spent my time on, and it's trying to give you a little bit of background about what you might ask me about. So since you're on week 8, you all know knowledge graphs basically connect entities, and they've got links that hopefully are labeled with hopefully terms that some computer and some human can understand. So we want to not only build high quality knowledge graphs, but we also want to build the terminologies that allow the knowledge graphs to function for what they were designed for, but also to live on and also to motivate other people to use them. So knowledge graphs have really been around a long time. There's a lot of documentation on how long they've been around. There's this one document from CACM that gives some of the history, but they really became popular when Amit Singhal wrote a blog from Google about introducing things, not strings. So from my perspective, which granted is a little biased because I live and breathe ontologies, and I love semantics, and I love teaching computers and humans what terminologies mean and how you might use them. But if you're going to move from a string, so just a set of characters, to something that is actually an object that might be connected to something else, that you might understand how it's connected to something else, I don't know of a better silver bullet than ontologies. So we need to, when we design these knowledge graphs, we need to also design those terminologies. So the ontology really kind of enables moving to things, not strings. And it can be anything from just a set of terms and definitions for those terms to structured knowledge. I usually write my ontologies in OWL, the World Wide Web Consortium's recommended standard for ontologies on the web, but really I'll take it in any kind of language that that can be described to me so that humans can understand it and computers can understand it. And I've sprinkled references along the way if you want to go back and look things up. And actually this paper that I mentioned here takes every dot on this spectrum and says how you might use a vocabulary or an ontology with that level of expressive power. So what does it really take to build a knowledge graph that others will use and potentially more importantly, that others maintain? So from the early days of my work in artificial intelligence, I always literally try to put myself out of a job, out of the current job, so I can move on to the next thing. So I want to actually not only build a knowledge graph and ontology that is going to meet the requirements for what I'm trying to do, but I also want to make something that my people can use, whether it's me or my group, but then also that other people can use. And then better yet, that other people can maintain. Because actually, it often is the case that somebody like me, a knowledge representation expert, is brought in to build the schema, to build the formal foundations for what those terms mean. But we do it in all sorts of areas. So I'm published in areas like epidemiology, but also wireless spectrum and also mushrooms. And so it ranges to a lot of topics that I didn't start knowing a lot about, but then I helped domain experts, people who really know the language of the area, to encode the terminology in a way that can meet the needs of question answering systems. And then ultimately, you want the people who actually really understand the domain. Like I want those volcanologists to maintain the ontologies that I help them write about volcanoes. You don't want me doing that because I know some, but not a lot about that. So what does it really take to figure out what it takes to make a knowledge graph that somebody's going to use? So it better at least address the project needs and answer questions that somebody has identified as important. So it might also have integrated content in useful ways. So if I could just do it myself, well, maybe I will do it myself. But if somebody else has done a big project like Luna, building these enormous knowledge graphs, I don't want to spend the time to build that if she's got knowledge graphs that that meet my needs. But I also want to really understand what the knowledge graph is, what it contains, and how that content got in there. And then, of course, I want to have the right access right and the right licensing. So those are just some categories of what it would take for me to use the knowledge graph. But then what does it really take for me to maintain the knowledge graph? Because I'm going to give examples in a project that I think we're now in year 7, funded by the National Institute of Environmental Health Science, where we've got exposure experts and epidemiologists and toxicologists actually maintaining the knowledge graph, even though I and my team helped design the original foundations of it. So why would somebody maintain it? Well, my project depends on it. Maybe I've got domain knowledge that's useful for the curation and evaluation, like those people in those domains know a lot more about those domains than I do. Maybe my tools benefit from it. So in some of my other projects, some of my learning friends are using these knowledge graphs for training so that they can have them train their methods and test their methods. Maybe I need some extensions that the authors of the knowledge graph are not supporting. So for example, I use CEBI, chemical entities of biological interest. I'm not a chemist, I'm not a biologist, but I need it for this, this exposure and health project. And periodically, there are terms that should be in there from my perspective and actually from the chemist and biologist perspective, but they're not there. So I have to put them in my knowledge graph until they get it in there. So I might participate with them, and actually I do participate with them in extending their knowledge graph so that it better supports my needs. And then I also might need higher quality or different quality or more frequent updates. So what we really want to do is build those quality knowledge graphs. But what does it mean to have quality knowledge graph? So there's a lot of criteria. I just picked out 2 references, but you can find a ton. But actually, when I was doing homework for this talk, I'm not convinced that there's like a single authoritative source of assessment criteria for knowledge graphs. And part of that is because the quality assessment is really aimed at the fitness for purpose. So what does it really take for this knowledge graph to fit my purpose? And so what does that really mean? It really means it fulfills some set of requirements. So from here on, I'm going to talk about some methodologies and some examples for building the knowledge graphs and for building the underlying terminologies that those knowledge graphs rely on. And then give some examples of those methodologies and update approaches. Because if you don't think about the updates, you're just going to have stale content. So we've got this ontology and knowledge graph development process that we've used for a whole lot of applications. I'm going to exemplify it by CHEER, the Children's Health Exposure Analysis Repository, where I'm a co-PI with some epidemiologists and some toxicologists and some environmental health scientists. I run the data science core, so my job was to build the terminologies that would allow a system to support integration of a lot of content about experiments of exposure and health outcomes to enable meta-analysis, to enable putting together content from multiple studies to try to figure out, say, does cadmium, exposure to cadmium when a mother's pregnant or sometime young in a child's life, whether that impacts development. So what do we do to start with? Really, everything kind of starts with a use case. What questions are you trying to ask? What's hard about answering those questions? What information do you need to answer those questions? And then what kind of vocabularies can I use as starting points? I've been doing ontologies not since they started, but since I guess I've been doing them since they just kind of started to become really popular in computer science. And in the old days, decades ago, it wasn't the case that there were already 100 good ontologies or vocabularies that were computer accessible, that somebody else maintained. And so it wasn't uncommon to have to build your own. But today, you're almost always making a mistake if you don't go out and look for existing vocabularies that often somebody else who really has a stake in the content maintains, and you can usually get really good starting points. So go out and look for the existing vocabularies. And the vocabularies are not just in something like BioPortal, which actually is a collection maintained at Stanford that started out being a collection of biologically oriented vocabularies, but kind of expanded to be a collection of a lot of different ontologies, about a lot of different topics. And that's just one resource of collections of ontologies and terminologies. But there's a lot of other places that you can get these terminologies, like the data reporting templates or data dictionaries and code books. If you work with people who do experiments, they usually give you Excel spreadsheets. When you're lucky, those Excel spreadsheets have column headers that have some definition associated with them. And sometimes they have codes in those categories. And if you're lucky, you get a code book that tells you what the codes mean. So there's a lot of different places that you can get your vocabularies. Then anybody like me, semantically oriented people, we have a lot of our own tools for extracting that content and putting it together and integrating it. But there's commercial tools that do that. There's a lot of academic tools. We at RPI have a bunch. When I was at Stanford, we had a bunch. And then we generate the ontology from leveraging existing content and kind of gluing together as we need to address the use cases. And the use cases will include competency questions. So questions that need to be answered for the application to be successful. And then in this example, we also put this into a human-aware data acquisition framework. And then we created knowledge graphs that are open to, so there's access control on them. So if if the people haven't published their results yet, then the data is not public. But once they publish the results, and the data is public to anybody. And until then, the data is public only to the people who have those rights. So everything starts with the use case. And this, I teach a class, or I co-teach a class on ontology engineering, and there's a book that actually was on that first slide that also has pointers to this use case template. So this use case template kind of has a lot of input from NIST. It has a lot of input from the National Institute of Standards and Technology, a lot of input from USGS and a number of kind of geophysical use case people, and a lot of input from my co-author, Elisa Kendall, and from OMG, the Object Modeling Group, and EDM, the Enterprise Data Management Group, to get in. What are you trying to, what kinds of questions are you trying to answer? What's your goal? What are the requirements? And then one thing that's incredibly important is get these competency questions down, because I love to build ontologies, and I will build them probably for the rest of my career, but you really want to have some way to scope. How do you know when you're done? How do you know what level of granularity to go to? And how do you know what your starting points are? So we've got a lot of links here. And also in this class, there's links to filled in templates for the use case as well. So you start with that use case, and then the use case helps try to figure out what kind of terminologies we need. And in this case, we heavily reuse a lot of existing ontologies. And what we did is we looked carefully at all the use cases. We tried to understand the questions that they were asking. We figured out kind of the breadth and depth of content that we needed. And then we figured out ontologies that covered a large percentage of what we needed. And those we wanted to import in. So we wanted to pull them into the vocabulary itself. And then we also identified a lot of large ontologies, such as CEBI, Chemical Entities of Biological Interest. So in this project, I need about 5% of this, and it's big. So I don't actually want to pull the whole thing in to build this enormous terminology. I only want to bring in what I need. So I use this approach, this minimum information to reference an external ontology term, or myriad. So this is typically what you do on these big external ontologies. So we really want to reuse where possible. And then we really want to have a strategy for that reuse, and we really want to communicate it. So one of the bottom line takeaways from this talk is to have a strategy for everything and have documentation kind of for everything, so that other people can follow the processes, and so that you have some kind of consistent usage of the processes. So we've got this kind of large spreadsheet that has a growing number of ontologies that we thought had some kind of overlap. And then we had a little description, and then we gave priorities for when you use those ontologies. And we gave that to the humans who were trying to do the mapping. And actually, it's interesting, Luna mentioned this schema matching. I agree. It's not ready to be done automatically, but it is ready to be done semi-automatically. So we've got tools that suggest mappings, and then we feed in this spreadsheet to the tools that suggest which ontologies to look at first with higher priority. And we also give that to the humans so that they can figure out what to use for mapping. And then we also have a process for how we're going to evolve the terminology. So when we started this project, we said, great, we have to do all of human health and all of exposure. Well, I might be busy for a long time, but I can do that. And then I talked to the lead epidemiologist over the project, and she said, I looked at SNOMED, the standard medical nomenclature, and I'm not going to need about 80% of that. And I looked at this other thing, and I'm not going to need that. So what we decided to do was kind of do an empirically driven approach. So when studies came in, if they had vocabulary terms that we didn't know, then and only then did we go out and try to bring those terms in. So we identify the terms that we haven't seen before. We identify how it can be mapped. So we've got this process. And actually, this process was generated by the epidemiologists. And it's reviewed by stakeholders. And those stakeholders I ran the Data Structures and Standards Working Group for the National Institute of Environmental Health Science, but the people who were making the decisions were the environmental health scientists and the toxicologists and the epidemiologists. So they weren't really the ontologists. We were just the people who kind of made sure everything made sense. Because what you ultimately need to do is you need to take these spreadsheets that you're getting with these column headers and say, okay, well, what am I going to map gauge to? Gauge is actually gestational age at birth. But I might not know that, but I need to map it so that I get this coherent, integrated knowledge graph. And we use this semantic data dictionary approach that helps humans and computers do that kind of mapping. And then it powers this system that you can see the number of studies, and you can do searches for studies that say have pairs of mothers and children who have delayed cognitive development, and mothers who were exposed to, say, 3 heavy metals that I might be interested in. And so I can retrieve either the studies or I can retrieve individuals themselves so that I can do a statistical analysis. So like this is one of the competency questions that a biostatistician gave us. So we wanted to look for children who have we've got data on the birth weight, the gender, the gestational age at birth, information about the mother, and then exposure. And you can do kind of a smart search that's ontology-enabled faceted search to retrieve that content. Vinay, how much time do I have?
About 5 minutes.
Okay. So I gave my examples on exposure and health, but that's really just one example. We're also doing this for IBM's AI Horizons effort to try to do precision medicine to empower. It's a HEALS project, health empowerment using analysis, learning, and semantics. So in the middle is the knowledge graph and the ontologies, but content comes in through learning algorithms, through extraction. We do all sorts of different reasoning on it. And then people can ask questions like, if my A1C, which is a marker for diabetes, has gone up 20%, and I've got the following features, what are my next steps? And we also consult to like a giant insurance company that's trying to support an individual health record. We do it in radio spectrum, trying to figure out when I can use spectrum. We support the financial industry, business ontology, and all sorts of other areas as well. I'm not going to go into this because of the time, but one take-home message is document all your processes. And I think the EDM Council has done a really nice job, and I provided the links. They give you a lot of information about how to develop your use case, how to build that terminology. One thing that they do is include a hygiene test. So there's a lot of principles that your ontology should follow, and then there's tools that automatically support that. I worked with EDM and OMG so that now all my ontologies also run those hygiene tests as well. And they also document how to contribute, like how to participate. So this is for their FIBO, that's a financial instrument business ontology. It's gaining a lot of traction and it's been around for a while. So I don't know how many people have contributed to it, but there's rules for contributing, and there's rules for annotating your content, and there's rules for how to determine your maturity level and your code of conduct. So there's a lot of process recommendations. So in the remaining 3 minutes, I'm going to give some pieces of advice for developing and for longevity. So get good use cases and design against them. And you do that maybe most importantly for scope and evaluation criteria. And then don't ignore the update requirements. Get those requirements in your initial use case and think about them when you're doing your schema build and your data acquisition. And remember that you might need to update your schema, but you might also need to update the data. And then potentially your application. So a lot of my applications run on Sparkle queries, and those Sparkle queries are using the underlying vocabulary. So I might need to potentially update those queries as well. So I need to have basically update plans for all 3 of those entities. And then it really helps to have style guidelines, because you really, one of the secrets that I think led my my wines ontology live such a long life was, one, it was pretty simple. Two, it was really useful for a pedagogical tool, and it was very consistent. So it was pretty easy to understand. So I said, strive for consistency, and then really reuse where possible. But remember that if you're reusing other people's work, you may be in conflict with your own consistency, because option one and option two, I might need to put together, but they might have different rules for how they model. So I might have to make some trade-offs. Err on the side of simplicity to begin with, and modularize along the way, and document definitely everything. And then when you're designing your ontology and your schema, first meet your requirements, but also think about reuse from the beginning. So like one thing that I spent decades doing is getting rid of restrictions in my core ontologies, because if I have too many restrictions, then that limits my reuse. So what I usually do is I pull the restrictions out, I put them in a separate module, and I consider those modules as kind of a quality check. So for example, rather than having a range on a property like has age, like humans might have an upper range, say 120 or 130. But if I have has age on domestic cats, 130 is too high. So it would be lower. So I would put those ranges when I use that property on a class rather than just on the property. And then also take advantage of all the evaluation environments that are out there. So in the notes, I've got links to Chimera, which was actually an ontology and knowledge graph evolution environment that I did when I was at Stanford, and OOPS out of Madrid, and the enterprise data management people, their hygiene tests. And then definitely think about unanticipated use. And with that, I will take questions, and there's a lot of people who contributed to this. And there's some books for reference on building ontologies. And, I didn't say that much about provenance, but definitely keep track of where you got the content, because that often makes or breaks your reuse. So I'll end there.
Excellent. Thank you. Thank you, Deborah, for such a illuminating overview of this whole field of this discipline of building ontologies for longevity and reuse. And yeah, so that's great. So we've got about 15 minutes or so for discussions and questions. And Luna has been great in answering the questions that were typed in the chat. So I thought I'll start the discussion by asking Luna a question. Do you have any ontologies in your product knowledge graph?
Yes, we do.
Could you tell us a little bit about those?
Yes, so I recall that when I talk about the AutoKnow system, we start with the input where we have the taxonomy. That's part of the ontology regarding the entity types or product types. And we also have an existing catalog, Amazon catalog, which says for each product, there are these attributes. And those, in a sense, are describing the relationships between the entities. So those are kind of the ontology we start with. And then we could extract more product types from the product titles, etc., from queries, and then we could decide the subtype relationship. Those are used to enrich the taxonomy part. And then for the relationship part, we look at customer behavior logs, especially their search queries, to decide for each product type, product category, what are the attributes that apply to it. And then we could make sure we add some sort of restrictions to the relations.
Yeah, so it seems that the ontology that you just described is probably on the lower left of Deborah's spectrum, right? It's clearly useful, but it's very close to the data and the usage, right?
I feel first it is very useful because that's kind of, that's the schema of the data for a database. Without schema, you can't have this database. And similarly for knowledge graph, without the backbones, you won't know how to put the flash basically. And so it is very useful. And the second thing is for many domains, luckily, we can sort of manually sort of develop the ontology. For some super complex domains, product domain is absolutely one of them. Just manually develop the whole ontology is just incredibly hard. It's a lot of work. Plus, it is evolving over time. And so we need to be creative to combine which part is really the core. And I really like what Deborah was saying. We need to give it less constraint, make it easy to extend. We possibly need to make sure it is absolutely correct and nothing wrong. And then when we extend it to the sort of surrounding part or outer sort of ring, we want to automate it so we can easily capture the change of the real world.
Okay, so I think a flip question for Deborah would be that, say if we came to you and asked your advice on, well, we want to go from 0 to billion, how should we go about it? What would your advice be for that? Or how would you approach it?
Well, I'd probably go to Luna. But actually, one of my students did an externship with a company I won't name, but and it wasn't Amazon. They also wanted to build a product catalog, so they did kind of lightweight entity extraction, and they basically got a set of properties, and classes. Actually, it reminds me of the vertical net days. So maybe I'll just talk about that, because actually when I was at Stanford, I consulted to Vertical Net, which was trying to build many verticals. So like they did drill bits, and I think we had 20,000 terms in our drill bit ontology, but NIST had a good starting point for it. So when we were doing that, we actually had a lot of vocabularies that were starting points, and then there was kind of this ontology czar. Actually, I kind of consulted in the ontology czar for how to help put those things together. And so they did it more manually, but they looked for the starting points. When my student went to talk to this startup company, they were looking, I think they were looking kind of to compete with the Amazons of the world for properties that you were going to use to figure out how to specify what you were going to buy. So what are the properties that, like, if I'm going to buy a TV, I care about the diagonal, maybe I care about the manufacturer, maybe I care about the price, maybe I don't care about some other features. So they looked at ways using entity extraction to just get properties of interest. They didn't do much to try to get the range restrictions on those properties. They did a little bit on the numerical ones. And actually, they had surprisingly good effectiveness just for kind of commercial products.
Yeah.
And actually, I'm in another program. I'm in the DARPA Machine Common Sense program. And the language models are just killing it in that domain. So I'm frustrated in that program because the language models are doing so well at answering what DARPA and Psych and Allen Institute think are reasonable questions for a common sense domain. But I don't think they're doing either what Luna was trying to do or what either my student was trying to do or Vertical Net was trying to do. I don't think they're doing like the precision search. They're just doing kind of common sense questions like, can an elephant walk through your front door?
Okay. Naren, Mike, do you guys have anything you guys would like to ask or contribute?
So I remember from the eBay days, we incentivized sellers to actually map their item to a entry in the catalog. And they had some incentives like the search ranking would be a little bit better and they could pay a little bit of less listing fee or something like that. So I remember those kind of things. Do you get the question for Luna? Do you use similar techniques to incentivize sellers to do something like that?
Yeah, so I have to say, first, Amazon is trying, and the second, Amazon is not super successful in this yet. So for retailers, sellers to enter the information for their products, they do have a whole bunch of information to fill in. I mean, like all of the attributes that apply, they can fill in. But on the other hand, Amazon realized that if they ask them to fill in too much information, it is not very friendly, and sellers really don't want to do this. I often make this point. I mean, for sellers, their goal is to sell their products. Their goal is not to help Amazon maintain the best catalog in the world. And so they really try to skip as much as they can. And we asked for a few fields they absolutely need, and most of the sellers wouldn't fill anymore. So that's what we get. And we try to show, hey, with the structured information, we can give you better results, we can improve search, we can show better choices. But still, so far, we are not super successful in terms of engaging them. Another thing we try to engage them is that if we find mistakes, they give us mistake information on the other hand. If we find the mistakes, we will send them back. We will ask them to fix. So far, that is still ongoing. If for some like serious mistakes, we will overwrite as far as they do not respond. And for not so serious mistakes, we will basically wait for them. So those are still ongoing efforts.
Thank you.
Thanks.
Cool. Mike, you're muted. Your computer is muted.
Yes, no longer, however. Yes, I was intrigued by a couple of things. I saw Luna talk about generic knowledge graphs versus product graphs. And I've heard Deborah talking about ontologies versus knowledge graphs, or are they the same? Are they different? I was wondering if I could get a crisp statement from either one or both of you about that distinction, first of all, between ontologies and knowledge graphs. And then I have a second question about products that's related, depending on what you say. That I'll have a second question. Anyway, so what's the difference? What's the difference between an ontology and a knowledge graph, Deborah?
Yeah, I don't think there's a succinct answer to this, because it's the same question as what's the difference between an ontology and a knowledge base, or what's the difference between a T box and an A box.
But you met in that room, that hotel room, the night before you were giving your talk. So did you get an answer to this?
Well, basically some people believe that you can only really have the terminology in the ontology, and actually, but I take a more progressive or a more accommodating position. And one of the reasons I do that is because in almost all good ontologies, there's some kind of special individuals that they're used so often that they really belong in your terminology. And so once you get a couple of individuals in your ontology, then I don't know where that break is. So, it's clear that the knowledge graph has instances, a lot of instances typically. It's clear that the ontology has class definitions and property definitions, and usually a few selected individuals. And I just actually participated in a book for this, and some of my co-authors wanted to take one of these positions, and I said, I'm going to allow this spectrum. Some people say that the knowledge graph includes the entire ontology. Some people believe that the ontology with the term definitions is over here, and you use those terms as you need them in the knowledge graph. And usually some instances make it in. So sorry, not crisp.
So, but you did say something earlier, which you talked about the definitions just then. And, a knowledge graph is, of course, a set of links and nodes, but I don't see the OWL there or the data log there, as Vinay was talking about the other day. Is that part of the ontology or not part of the ontology? It doesn't seem like it's part of the knowledge graph. It's kind of an annotation on it in some way. But.
Yeah, so we also have a knowledge graph infrastructure, and we basically have the ontology in one knowledge graph. and then the knowledge graph that's got all that instance data that uses terms from the ontology in the other one, but you could put them all together.
Yeah, so I would like to second that in the knowledge graph, in the graph, you can have both data and ontology. I mean, a type, an entity type, which is part of the ontology that can be part of the graph. And actually in my first example for the two songs, we see a node represent a genre, we see a node represent recording, and those are actually ontology nodes. And I can just speak up for what I observed at Google, at Amazon. So for me, for a knowledge graph, it contains two parts. One is ontology, one is the real data. And the ontology describes what are the entity types, what are the relationships between the entity types, and also the constraints. And the data part gives all of the entity instances and all of the relation instances. And we could say, hey, electronics, this is a type, this is part of ontology. And then a particular electronics like an iPhone product, that is the part of the data. I don't know if Deborah agrees.
Yeah, I like that. And actually, going back to Mike and the that room, if you go back to the ontology spectrum, there's this big red bar of the stuff that has the formal ISA restrictions. Everybody agreed that the right of the big red bar was an ontology, and some people believe that the left was.
Okay, that's good. I have another question, which is knowledge graph. So this it probably is in somebody's knowledge graph. It's made by 365, sold by Whole Foods, Amazon. So that is probably a node in somebody's knowledge graph.
Yes.
But wait a minute, not this one, but some actually have a number. Each can has its own individual number.
True.
So the question is that is that going to be a knowledge graph, or is it just the fact that if you're numbered between M, X, and Y, you have certain properties you were manufactured in this particular place, and so on and so forth? How do you deal with true instances?
Yeah. So for Amazon Knowledge Graph, product graph, we do not distinguish that. And all of these products, except that ID is different, everything else is the same.
Right.
And our sort of goal is to tell customers, if you want to buy this, hey, this is a brand, this is like the material for the sort of a holder, et cetera, and we don't need to distinguish at the number level. And this really applies depends on what are the applications. We can go one level up. Do we say, hey, these are all, shall we have one entity for all human beings, or we want to have a different nodes for different human beings? And normally we do, because we are so different.
I'm glad to hear about that.
All right. Maybe that's a good time to conclude, because we are pretty much at the end of our class time. So with that, I'd like to really thank both of our guest speakers, especially Deborah, because she's in her vacation and she took time out of her vacation to be with us. And of course, it's always inspiring to hear Luna talk about Amazon's product knowledge graph, because it's a real thing. People use it. I use it lots of time during a day. So Luna, thank you so much for taking the time out of your busy schedule. It's been very educational for me, and I'm sure class really appreciates that. So with that, we will conclude, and the class will continue on Thursday. And on Thursday, we have another guest speaker, Frank McSherry, who will be telling us about incremental view maintenance. And Frank is actually a winner of the Girdle Prize. So it should be an interesting session. So thank you all very much, and we'll see you later.
Well, thank you.
Thank you.
Thanks much. Good seeing you guys.
Bye.
Bye.